Swayam Prabha. Digital India. Educated India.
So again I plot VC versus time. So like I said initially, VC is at a value Vp. Okay, and also for convenience I will redraw this circuit with Vs equal to 0. Okay, with Vs equal to 0 it's a short circuit. And I have this C and R, and the voltage across this is Vp at t equal to 0. Okay. Now what will be the current through the capacitor? Okay, so let's say I call this as IC, and because Vs equals 0 I have shown it as a short circuit. So if the capacitor current is flowing like this, I have used the passive sign convention. What is the current IC? So there is an answer Vp by R, but please mind the signs, because I have used passive sign convention for IC, so flowing from top to bottom. That's right. First of all, the voltage across the capacitor and the resistor, they are the same in this circuit. They are in parallel. Okay. So this voltage with this polarity is Vp at t equal to 0, which means that a current Vp by R flows in that direction. So this IC, which is the current flowing from top to bottom in the capacitor, is minus Vp by R. Okay. Okay. So what happens to the capacitor voltage after t equal to 0? Capacitor voltage Vc for t greater than 0. What happens now? Will it increase or decrease or remain the same? So that's right, it's going to decrease. Okay, so it will decrease, and the slope is again given by the capacitor current. Okay, minus Vp by R is the capacitor current, C dVc by dt. So dVc by dt is nothing but minus Vp by Rc. Okay, so the slope is minus Vp by Rc. Okay, so there was a question here that was whether after charging a capacitor to some voltage, can we use it as a voltage source? Yes, we can. In fact, it is used like that in some cases, but of course you have to remember that a capacitor is not a voltage source. As you draw current from it, its voltage is going to change. Okay, so after some point the voltage changes so much that you can't use it anymore. Okay, so let's say you have you want a 5 volt source. You can charge a capacitor to 5 volts and use it, but as you draw current from it, the voltage will start decreasing, and at some point it may go so below 5 volts, so far below 5 volts that it may be useless. Okay, but in fact this is used if you want a source for a very short time where you are not drawing so much charge or so much current from the capacitor, you can use that. In fact, in many electronic gadgets, when you want to change batteries, okay, during the time you take to change the battery, there will be no source. So some of those gadgets may use a very large capacitor, okay. So in the time that you take to change the battery, the capacitor will be acting like a voltage source and supplying power, okay. But of course, it cannot do it indefinitely. So if you leave it without batteries for a long time, it will just discharge and die out, okay. So the slope is minus Vp by Rc. Now let's say we come to this point, okay. So what happens to the slope after that? What happens to the current through the capacitor, and what happens to the slope of the voltage across the capacitor? The voltage across the capacitor is decreasing, but after it decreases a little bit, what happens to the slope of the voltage? Now clearly, the voltage across the resistor is also Vc, and as Vc reduces, the voltage across the resistor reduces, which means that the current through it reduces. And if the current reduces, okay, the slope of the voltage also reduces. So it does that, and then does that, that and that, and so on. Okay. So finally, it turns out that it will asymptotically reach 0, because the input is 0 for t greater than 0, and if this capacitor voltage goes all the way to 0, then there will be no current through the resistor, and that means that the capacitor voltage cannot change at all, which in turn means that the capacitor has reached its steady state. Okay. So this asymptotically goes to 0. Okay. Is this clear? Any questions about this? Okay. So now we have looked at the behavior of the capacitor voltage for two cases, when the input jumps from 0 to Vp or from Vp to 0. Qualitatively it is the same. It starts changing with a certain slope, the capacitor voltage, and the slope goes on reducing. Okay, the magnitude of the slope goes on reducing. So it starts off steeply and then becomes less and less steep, and finally asymptotically reaches some value. When you change the input from 0 to Vp, that value is Vp. When you change the input from Vp to 0, that value is 0. Okay, this is fine. So key things to remember are that are the values of the slopes and so on. Okay, so this slope is minus Vp by Rc. Okay, so it starts from Vp, and if it went like a straight line with that slope, it would cut the time axis at t equal to Rc. Okay, but of course it doesn't do that, because the moment the voltage reduces a little, the current also reduces, so the slope reduces and so on. Okay. So now, what do you think this shape is? We have done it intuitively and graphically, but we have to also be able to write a formula, an expression for Vc as a function of time. So what is that function? Any guesses for what that is? So let's see. Let me take the second case where the input Vs was 0 after t equal to 0. Okay. Okay. So for t greater than 0, this is the model with Vs set to 0. Okay. Now let's see what shape it is. Somebody answered parabola. It turns out it's not a parabola. The differential equation governing this is Rc dVc by dt plus Vc equals 0. Okay. Now I will rewrite this as dVc by dt is minus 1 by Rc times Vc. Okay. So what this equation is saying is that the derivative dVc by dt is proportional to the function itself. Okay. So the derivative is proportional to the function. So what is a function that gives you a derivative which is essentially the same function? It may be a scaled version of that function, but it is the same function. Okay. So for instance, let me do it with some other variables. I could have something like this. If I have dx by dt equal to x, okay. So in this case also, the derivative is proportional to the function. In fact, I have made it exactly equal to the function. Now you know how to differentiate functions. So what is the function that you can recall that has the derivative which is the same function? Please try to answer this. Derivative is proportional to the function or maybe even equal to the function. What is the function that meets this criterion? So if you want, you can think of the table of derivatives that you would have studied when you studied calculus. So think of a function whose derivative is the same function. So clearly, an exponential satisfies this because the derivative of the exponential is also an exponential. Okay. So now, let's say I don't want the derivative to be equal to the function, but only proportional to the function. Okay. So I also know that if I had a scaling factor here, exponential at, and I differentiate it, I get a times exponential at. Okay. So clearly in this case, if Vc is as an exponential, this function will be satisfied. Okay. Also, I want a particular scaling factor, right? So you see that this equation is of the same form as this. Okay. So the derivative of something equals a constant times the same function. Okay. So what is a function that will satisfy this? Satisfy this equation. It is Vc of t of the form of exponential minus t by Rc. Okay. So clearly now I also can have a scaling factor here. So let's say V0, because that will cancel out. If Vc of t is V0 exponential minus t by Rc, please give me the value of dVc by dt. What is dVc by dt? If Vc is V0 exponential minus t by Rc, I use these expressions to find out exactly what goes inside the exponential. If it is exponential at, the multiplying factor here is a. I want the multiplying factor to be minus 1 by Rc. So a has to be minus 1 by Rc. So Vc of t is V0 exponential minus t by Rc. Okay. So just differentiate this and tell me what the value is. Clearly, this is minus V0 by Rc exponential minus t by Rc. Okay. So you can see by inspection that this will satisfy this equation. Okay. Because the derivative is minus 1 by Rc. Okay. So this part of it times the rest of it, which is the function itself. Okay. So the solution to Rc dVc by dt plus Vc equal to 0. The solution to this is Vc of t equals V0 exponential minus t by Rc, and V0 can be anything. Okay, but as far as the differential equation is concerned, so any value of V0, this differential equation will be satisfied. Okay, but in our circuit we will need a particular value of V0. So how will we find this? How will we find the value of V0? So there is another answer which says V0 by Rc exponential minus t by Rc. I think you have omitted a minus sign. It should be minus V0 by Rc exponential minus t by Rc. Okay. So now we know that the shape of this blue curve here is of the form of V naught exponential minus t by RC. So this exponential describes the response of these types of circuits. Okay, and also we know that at t equal to 0, it starts from Vp. Okay, what is the value of this function at t equal to 0? The value of this function at t equal to 0 is, if I substitute t equal to 0 in this exponential, I will get V naught. Okay, but I know from the circuit that it's going to be Vp. So for this to correctly describe the blue curve here, this V naught has to be Vp. Okay. So this curve is Vp exponential minus t by Rc. Okay, is this clear? So if initially the capacitor had a voltage Vp and the input also had a voltage Vp, then the current through the resistor would be 0, current through the capacitor would be 0, and it would stay at Vp. But if Vs jumps from Vp to 0, then the output will slowly discharge all the way to 0, okay, towards 0. Now we have also determined that function. The function is Vp exponential minus t by Rc, okay, and we had intuitively determined the shape, that it has some slope initially and then it goes on decreasing, okay. And that's exactly what the exponential does. You please keep in mind that this exponential is the exponential of t but with a minus sign inside. Okay, so if you have an exponential with a plus sign, it will blow up. Okay, it will go on increasing with time. If you have exponential of minus t by Rc, it will go on decreasing with time. So any questions about this? The capacitor voltage across this will follow an exponential. I will redraw the input and output. Vs changes from Vp to 0, it jumps. Okay, so this is Vs of t, and Vc of t, we'll assume initially it was at Vp and it slowly goes to 0 like that, and this is Vc of t, and it equals Vp exponential minus t by Rc. Okay, and the differential equation governing this is Rc dVc by dt plus Vc equals 0, and the solution is Vc of t is Vp exponential minus t by Rc. Okay, so by now you should be comfortable with these results. If you have any questions at all, let me know. I will clarify that further. Okay, any questions about this? Now in this circuit, in this condition, the condition we are evaluating is with zero input. Okay. So if you look at this differential equation, it has only Vc. It doesn't have anything corresponding to the input. The input is 0. Okay. So such a differential equation where the input or the right hand side is 0. Okay. I will always try to group the variables on the left hand side and the constant inputs on the right hand side. Okay. Here Vc is the variable, and this kind of an equation which has a 0 on the right hand side and only terms with Vc on the left hand side. This is known as a homogeneous equation. Okay. So if you have taken some mathematics courses on differential equations, you will be familiar with this term. But in this course, whatever we need of differential equations, we will study them ourselves. Okay. And this response, because we have zero input, is known as the zero input response. Okay. And this term, which appears inside the exponential, Rc, this is known as the time constant. Okay. It also appears here as coefficient of dVc by dt, but we have to be careful. Okay. The coefficient of Vc has to be 1. In that case, the coefficient of dVc by dt will be the time constant. Okay. So it's called time constant because clearly Rc has dimensions of time. We have exponential minus t by something. So this has to have dimensions of time, so that we have exponential and inside that some dimensionless constant, dimensionless number. Okay. So this is called the time constant. Okay. Any questions about this? So like I said before, the initial slope is Vp by Rc. Okay. Now at t equals Rc, what is the value of Vc? What is the value of Vc at t equal to Rc? Please try to calculate this.